Thank you very much for the invitation to present my work here with such a big audience. So my presentation will be on a phenomenon that we've been researching called photochemical upconversion. And though we've used as our inspiration photovoltaics, I really think there's a bright future for upconversion beyond photovoltaics, because to transform the wavelength of light from a lower energy photon to a higher energy photon has many distinct applications and presents many opportunities. Now, I like to present this map because it's produced by, a pretty reasonable corporation. I shouldn't call it a corporation, entity, NASA, and it shows the potential for the deployment of solar energy around the world. And you can see that Tibet is blessed in that way, and Australia as well is the sort of place that really should be doing research into solar energy, and it is. And my colleague Gavin Conybeare here is in the audience, and UNSW, where I moved 18 months ago now, has been supporting work in solar energy for many years, much more than my previous institution. So let's take a step backwards and think again about how it is that solar cells produce energy. And I like to teach this to students in terms of a ratchet. So what we consider is a ratchet that can turn one step around on the absorption of a photon or unwind one step by emitting a photon, and the rates of absorption and emission are related by thermodynamical laws. So you can't really change rates, the rates K and K prime by just adjusting those parameters. They're linked by thermodynamical principles. So in order to get this ratchet to actually do work and sustainably work for you, you have to sacrifice a bit of energy, which I indicate here as Q. And of course, then Q diminishes the photovoltage below the bandgap. And so you can crank through these equations and optimize the rate of work, which is of course power. And when we do that, we reproduce the famous curve originally produced by Shockley and Kweisser in 1961. And so using a modern representation of the solar spectrum rather than a 6,000 Kelvin blackbody, we arrive at an absolute limiting efficiency for a single threshold solar cell under one sun of 33.7%. And that number will change depending on the exact spectrum you use. And that's at an optimized bandgap, right? So silicon with a bandgap of 1.1, has a maximum efficiency of about 30%, and if you take into account other processes like Auger, that will be reduced. Okay, so where are the efficiency losses? I like this plot very much, produced by my former colleague Ned Eakensdorks, who's now moved, now he's been in London many years now. And here he indicates the contributions to the full 100% of solar energy, or basically the fate of the 100% of solar energy as a function of bandgap. And what you can see is that for any solar cell, any single threshold solar cell with a moderately high bandgap, the absolutely dominant source of efficiency loss is the fact that you transmit photons below the bandgap. So here indicated as the below EG loss. For something with a lower bandgap like silicon, it's about evenly split between the loss due to thermalization of the photon energy in excess of the bandgap and the loss of photons below the bandgap. So I'll indicate here rough indications of bandgap, and you see that for amorphous silicon, OPV, and perovskite cells, which are broadly in this region, nudging up towards 2 volts, really the biggest target is the below EG loss, and silicon is down here. So that's the goal of what my colleague Martin Green coined as third-generation photovoltaics, to try to use the solar spectrum more efficiently. And there are various ways to do this. You can try to use all of the photon's energy through down conversion, which is something else that we work on, which is related to singlet fission as well. multiple exciton generation, which is a very nice concept, and hot carrier solar cells, which is also activity undertaken by colleagues in the Photovoltaics school at UNSW. Using the low energy photons, you've got two broadly researched strategies, which are upconversion and intermediate band cells. And today I'm going to talk about upconversion. So with upconversion, this is when you take photons below the band gap and convert those to photons above the band gap. If you can do this perfectly, and then calculate the efficiency limits using multiple ratchets and gears and so on, then you arrive at this solid curve here, right, which peaks up around 45%. And it's not that we really dream, well, we can dream of producing a 45% cell, but rather you see that with band gaps nudging up towards 2 electron volts, they are actually prime candidates to couple with upconversion. And so for many years we've been waiting for high efficiency cells with high band gaps, and indeed perovskite structures, for instance, present us with perhaps a real opportunity to deploy upconversion. And you can see that for crystalline silicon, upconversion would help, but it doesn't stand to gain the same as other technologies with higher band gaps. All right. So the exact mechanism by which we achieve upconversion is by fusing triplet states. We can call it triplet fusion amongst friends, but we'll never use the word fusion with the government. They get scared and run away. And fission is worse, of course. So you'll also see this called triplet-triplet annihilation, although strictly speaking, well, and both triplets go away, but the energy doesn't disappear. And so the way that we do this is we interact two different types of organic chromophore, and they have very different roles. One is called the sensitizer, and it has got ideally a very strong absorption at low energy, which allows it to absorb from its lowest singlet state, its ground state, to its first excited singlet. The molecule is chosen and designed so that it will undergo a rapid inter-system crossing to its lowest triplet state. Now what is key here is that the singlet and the triplet are close together so that we don't sacrifice too much energy. And this is essentially, again, a ratchet situation, because by locking off, by sacrificing a little bit of energy, what we can do is increase the longevity of the stored energy. Now we're in a triplet state which is metastable. So instead of nanoseconds, I've now got microseconds or up to a millisecond to do something with that energy. And what we do is we allow it to be transferred to a different molecule called the emitter, for reasons that will become obvious. And the emitter has got a different energy level structure where the triplet is about halfway to the singlet. And that large energy gap means that that higher energy singlet is actually itself highly fluorescent rather than undergoing rapid inter-system crossing. And so this is done 1 mole of times, right? It's not just 2 photons, but this is happening all over the material. And what we want is that it becomes statistically probable that 2 emitter triplets will come together and annihilate, placing one of the molecules into the excited singlet and one back into the ground state, from whence fluorescence emanates. And so this can be done. And here's a real picture from my lab. It's a laser beam propagating through a cuvette with a mixture of 2 different molecules in toluene. It's fairly simple. You just have to be able to deoxygenate and mix the two things together. So this is obviously a red to yellow system, but all sorts of color combinations are possible, and that's one of the real advantages, as I'll show you. So I mentioned other applications. Of course, photovoltaics is our inspiration and is what I'm going to be talking about mostly today. But we also have people working on drug activation. So there are situations where you might want to penetrate flesh, living flesh, for instance, with 800 nanometer light, and activate a polymer to degrade and release drugs using a shorter wavelength, which itself cannot actually enter the human body. 800 nanometers is a a really good tissue window. Biological imaging, if you can arrange upconverting nanocapsules, then you can get around autofluorescence problems in imaging. Solar fuels, this is an obvious one as well, related to photovoltaics, where often people that are studying the solar fuel production use actually very high bandgap materials. I mean, sometimes as high as 3 electron volts. In fact, the materials are sometimes white, right? So if you want to absorb sunlight, best not use a white material. This is something I just made up, but because we can upconvert wavelengths, we also think that maybe we can produce white light with a lower voltage than 3 volts. So rather than starting with a blue LED, we might get to some sort of compromise and light things up based on triplet annihilation. And also related to titania and high energy electrons is water detoxification. So this is just another representation of the processes that are going on, and you can follow through the way that the energy flows between ground state singlets, excited triplets, and transferred. It's using a different naming scheme here. The emitters are called annihilators. This was made for a paper that I published with one of the pioneers in this field, Phil Castellano. The picture was also made so that we could explain to biologists what we're doing. They like these sorts of things. So photochemical upconversion is nice because it's spectrally versatile. Here's just another picture. Okay, green producing blue. You can see red producing blue on the left. We can use near-infrared light. It just doesn't make very good photographs. Okay. The other thing, so we're spectrally versatile, and in principle, we can have very high quantum efficiencies. So what has been reported, the highest reported quantum efficiency from a triplet annihilation process in the literature is 43%, which is 86% of the maximum achievable, because in terms of quantum efficiency, right, we're always burning 2 photons to make 1. And so everything seems like it's poised to be applicable to solar energy. And so what we can do is imagine an architecture like this, all right? So on the left, we have a very happy sun. My postdoc chose this picture, and I like it very much. You have a solar cell where most of the spectrum is harvested by the cell, but it leaks through the red end of the spectrum. And we'll isolate what is necessarily a semi-transparent cell, and we isolate that from the upconversion medium, which is indicated in green. Upconversion proceeds in this medium and is emitted isotropically, and because of that, we need a back reflector behind the upconversion medium, and there's an optimum width for that. And you can get at least a factor of 2 improvement in the coupling with a simple back reflector. What is even better is the Lambertian reflector, because wavelengths that are poorly absorbed on the first pass by the upconversion medium can be scattered into longer path lengths within a thin film and are then absorbed, and this increases the absorbed photon concentration, and that, as you'll see in a moment, increases the efficiency. The dyes, because we're using molecules, they sometimes have what might be considered narrow absorption bands, but it's been demonstrated that you can actually make a cocktail, and you can make a cocktail to broaden the absorption right down to the lowest energy you can deal with. So there's no need to incorporate quantum dots or anything like that. Okay, so I'll show you our first couple of applications of this process to organic photovoltaics and also amorphous silicon cells. Just to give you an idea where we're at. So there's the depiction of the process again, and you can see the 2 species that we're using. On the left, this is a big, ugly, well, some people say beautiful molecule. It's a tetrakisquinoxylino porphyrin palladium 2 something something. It's made by my former colleague at the University of Sydney, Max Crosley. And we couple that rather bespoke porphyrin molecule to rubrene, which is a commercially available fluorescent molecule. It's even used in glow sticks for rave parties and things. There's a huge industry in rubrene, and OLED people know about it as well. But these 2 molecules go together rather nicely, because you can see that the porphyrin absorption has got a window in its absorption spectrum which allows the rubrine emission to come out. So if I'd used quantum dots or some other sort of material with just broadband, sort of heavy side step function like absorption, then I'd be reabsorbing my upconverted light. So I don't want to do that. I want to allow the upconverted light to escape, and so you can see that these molecules work rather nicely together. Below those spectra, you can see the characteristics of two organic cells which were made by Alexander Colesman and his co-workers. Alex is at this conference, so you might run into him. And you can see that these cells, I must admit, were made for us so that their absorption switched on more or less above the absorption of the porphyrin. So we're creating a situation which gives us a maximum possibility to see a positive effect. All right. So how does it go? Well, when we put the upconversion medium behind the cell and optically contact it, we can measure an external quantum efficiency curve with the upconverter operational and with it non-operational. And the way that we do that is by misaligning a bias and a chopped probe beam. So in a similar way to how solar cell scientists might flood their cell with white light, what we do is we create a continuous pump of the upconverter and then measure the response of the cell to a probe. And what we see is a ratio of the EQEs. And so the most impressive result is this 12% enhancement of the EQE in the presence of the upconverter. That's of course 12% of not much, right? So what we really want here is a figure of merit that has some sort of a meaning and that we can calculate. And so what we do is we say to ourselves, okay, well, what is the actual expected current increase of that solar cell? Right? So with the EQE ratio, we can simply multiply that by the EQE curve and calculate the delta J SC, so the extra current. And then we penalize ourselves, right? Because this is a nonlinear process at low efficiency. And so what we do is we divide our current by the square of the concentration factor. So in this case, I would divide by 29 squared. And we can see how we go. Just want to point out that the solid curves that you see superimposed on the experimental data, which are the circles, are a model based on a very simple equation that one can work out on a whiteboard in like 20 minutes. And so it shows that, that the shape of the curve is exactly what's expected with only one adjustable parameter, and that's the vertical scaling, right? And so this really shows us that what we're seeing is the effect of the upconverter. There's no other way that the spectrum of the absorbing sensitizer molecule could possibly imprint itself on the EQE curve of a solar cell to which it's only optically connected. All right, so let's look at that figure of merit and see how we've gone. So first of all, we wanted to compare it to rare earths, which is another way that upconversion is achieved. And we took an older study and measured from published curves what that delta J SC divided by C squared looks like. And it's right down there at 10 to the minus 6 milliamps per square centimeter per square sun, right? Ultimately, you want to do your measurement under one sun conditions, and so you can stop confusing people about what a square sun is. Our very first attempt at this, right, we were getting numbers around 10 to the minus 5 up to 10 to the minus 4. We're then able to improve the optical situation with back reflectors and so on. We ordered some new solar cells, and you see here that the best result is for an amorphous silicon solar cell, which was doctored in such a way that it better matched our molecules. And we're still down there at 10 to the minus 3 milliamps, right? So that's quite a small amount. Indeed, I've got to find 3 orders of magnitude improvement, which sounds like a formidable task, but hey, it means we can do more research. So let's go looking for this improvement. And I would say that, well, because this is real milliamps, which is produced by the solar cell, I can probably get my hands on a better solar cell at some point. I'll give myself a factor of 2 there. The dye absorption curve, it's only a single dye. We haven't gone for multiple dyes. We can probably get a factor of 5 out of that. But that's nowhere near the factor of 1,000 that I need to get up to device-relevant conditions, which would be around a milliamp per square centimeter enhancement under 1 sun. And so what we've really got to look into is the upconversion efficiency before we turn into engineers and really start to manipulate everything else. Let's go drill right down into the process. So to really figure out how efficient our upconversion system was, we devised this spectrometer, and I'll try to point and talk into the microphone at the same time. It's kind of hard to see it side on. See, basically what we're doing is similar to the way that we measured the solar cell. We take a white light beam and we split it into 2 using polarizers, and then we pass one part through a monochromator and a chopper, and that becomes our probe. The other part is placed through a filter and becomes a proxy for a continuous broadband pump. And we recombine these onto the solar cell, measure and lock in. And this allows us to measure a single wavelength response, but under 1 sun conditions, because this is ultimately what we want to know. And so we did these measurements now, took the solar cell away and just concentrated on the upconverter and looked at the efficiency of red to yellow. And the way that this experiment works is that it's internally referenced. Because without the modeling, you can see our model curve below, this complicated expression, but even without that, we know that we can excite the emitter molecules directly with the wavelengths that they like to absorb. And so in the graph on the right, the large humps on the left are indeed the direct excitation of the emitter. And so a rough guide to the efficiency can be seen simply by the ratio of the peaks due to the excitation of the sensitizer and the excitation of the emitter. And in both cases, we're measuring the emission of the emitter, right? And so you can immediately see that the efficiency here is rather low. What we expect to see under fully efficient conditions is that the peak on the right, which is blown up here, would be half as high as the peak on the left. So after modeling, what we find out is that under 1 sun conditions, this upconverter is only 1% efficient. So and when I say 1% efficient, I mean on a scale of 0 to 100. So the quantum efficiency is like 0.5%. So I need to go and find myself a factor of 100. Okay, so in the remaining time, I'll talk about the yield and how to increase it. And it looks like I have to talk rather quickly. So we can do some chemical kinetics and write down an expression for the concentration change of triplet states in time, and under continuous conditions, the change in time is 0, and we've got 3 terms. We've got a birth term due to the absorption of photons, and then a first order and a second order decay. So the fraction of emitters that undergo triplet annihilation is given by this ratio, which is the rate constant for the triplet annihilation times the triplet concentration divided by K1, which is the intrinsic decay of the emitter, plus K TTA times the triplet concentration. So what you can see from that is that we need to get F up to 1, which means we need to increase the triplet concentration. A simple expression for the triplet concentration, at least under low efficiency, and obviously, we don't really care about the expression under high efficiency, because if we were there, we'd already be jumping up and down and buying champagne. We've got 3 terms. We've got K phi, which is the rate of photon absorption by the sensitizers. We've got the concentration of concentrate the sensitizers. We need to concentrate the sensitizers. Or how can we address the lifetime of the triplet emitter? Okay, so I'll talk about these very briefly. So we have tried to address the rate of photon absorption with some rather badly engineered retro-reflecting back reflectors, and we were able to demonstrate a better than 2-fold increase. And if anyone out there that can do this better and make nice micro-imprinted mirrors, I'd like to talk to you, and we can do this properly. Our theoretical modeling shows that we could get up to a 9-fold increase simply by optimizing a back reflector with parabolic dishes which would locally concentrate the light. And we published this in SPIE journal, which I encourage everyone to do. To increase the concentration of sensitizers, it's not so straightforward because organic molecules like to aggregate. And so what we devised was a system whereby we would ligate sensitizers to a nanostructure and try to perform then the upconversion in the excluded volume. So there's a cartoon on the right which I used to convince the Australian government to give me money. They were fooled. All right. Now, if we look at how much we have to concentrate the sensitizer by, I can put in some very reasonable rate constants for TTA, about 10 to the 9 per molar per second, K1, typically 10 to the 4 per second. And that tells you to get F up to a reasonable number, we need the triplet concentration to be 10 to the minus 5 molar, which is kind of high. And to do that, with typical rate constants for the excitation, dyes absorb about once per second under 1 sun. It means that we need the sensitizer concentration to exceed 0.1 molar. Okay, well, we set about doing this, and we did some real chemistry, sticking these sensitizers onto kind of nanoballs of silicon. And we then had to investigate, well, would we be able to get the triplets off the surface and do the sensitizers self-quench? And actually, we found that by adding, in this case, rubrene sequentially to higher and higher concentrations and monitoring the kinetics of the phosphorescence, then if you follow the black dots, then above a certain concentration of rubrene, we've essentially taken all of the triplet states off the surface, which is nice. But when we look at the performance of our nanostructure, again, now, with an amorphous silicon cell, we find that our figure of merit is indeed less than solution. So why is that? Well, if we drill down into the kinetics of the upconversion and look at our rate constants, our decay rate of our emitter molecules, right, with the nanoparticles, with these dressed nanoparticles, be they concentrated or dilute, is much, much higher, maybe 3 times higher than a reference upconverter. And the reason that this is what I believe is that when the emitter triplets are in the vicinity of a nanoparticle with a high concentration of sensitizer, they experience an external heavy atom effect. And so indeed, you would get an augmentation of K1 by a term that grows linearly with the concentration of sensitizers, and then that kills us. In fact, one can then model how the upconverter will behave with such an equation, and in fact, there ends up being a sweet spot in the concentration, and it's not quite high enough. So what we're going to try, and we're working on this now, is to substitute palladium or platinum, which are indeed extremely heavy atoms, with zinc compounds, where we might only get 90% triplet yield, but the heavy atom effect is diminished. Okay, Phonon Engineering, well, this is a fancy way of saying changing the vibrational structure of a compound. It's well known within the chemical physics community that if you deuterate certain compounds, you can increase the lifetime of electronic states that otherwise suffer non-radiative effects. And the reason is because non-radiative phenomena in molecules are immediately isoenergetic, and to soak that energy up, we need to put it in molecular vibrations. And there's a vibrational wave function overlap factor there, which is diminished by orders of magnitude, hopefully, by deuterating and replacing hydrogens with deuteriums. And so we have shown, and I believe that our experiments were poor because the effect is not as pronounced as I wanted, but the effect is there, and it's clear that one can increase the lifetime of triplet states with deuteration. And this shows that there are prospects for doing, if you like, phonon engineering of emitter molecules to promote the lifetime and increase their efficiency. And in the remaining 60 seconds or so, I'll just talk about a few other things, because undoubtedly someone will ask me about moving upconversion into the solid state. because so far we haven't shown efficient upconversion in a real solid. But what I can tell you is that the upconverter that you see being irradiated here is really upside down. Right? It's not that the rest of the image is upside down and I'm fooling you. That is a gelled solution which behaves in most ways like a solid, or at least a quasi-solid. When you dry it out, you can see it's actually made of spaghetti inside, but the spacing between the strands of spaghetti is much longer than the length scale for upconversion. And indeed, our hypothesis was that we would not hinder the upconverter much at all by having a gel. And when we look at the characteristic excitation spectra, they are the same, and the efficiency of this system is just identical between liquid and a gel. And because it's a green to blue system rather than a red to yellow system, we can actually achieve much higher efficiencies under 1 sun of 7%. I've more or less run out of time, so I can just tell you that one other way of addressing these issues is to move to 2 emitters, where we can kind of synergistically take the characteristics of one or the other, and we've done these experiments and we've been able to improve the figure of merit beyond 10 to the minus 3. And so maybe if you ever get to hear me talk again, we'll have improved this further. There's certainly scope for it, plasmonic effects and so on. And my very last slide is here. I just want to advertise work by one of my colleagues at the University of Wollongong, who is, instead of relying on the emission of light by the final electronic state there, he's made a dye-sensitized solar cell which injects that electron directly. So it's indeed maybe something like a molecular intermediate band solar cell. And with that, I'd just like to acknowledge all my co-workers and my source of funding, the Australian Research Council. And thank you for your attention.